Hey, so I'm Amanda, and this is my group, Kevin, Rohan, and Dan, and our project was propane to acrylic acid. As process design engineers, we do not build prototypes, but instead conduct feasibility studies using computational methods such as Aspen. These feasibility studies are then created into processes which make the compounds produced for mechanical and electrical engineering product design. In our process, we analyze the industrial scale production of propane to acrylic acid using a mixed metal oxide catalyst for which patent information is recently available. We've determined that this manufacturing process is in fact profitable as proposed. Now let me tell you a little bit more about why it's important. Acrylic acid is used in a variety of consumer and industrial goods. There are two commercially available grades of acrylic acid, technical and glacial grade. Technical grade is approximately 94% purity by mass and is used in paints, textiles, sealants, and adhesives. Glacial grade acrylic acid is approximately 99.8% purity by mass and is used in superabsorbent polymers such as diapers and detergents. Our process will be making glacial grade acrylic acid because of its high purity and high selling price. The current market for acrylic acid is approximately $11 billion per year and is growing at approximately a rate of 3 to 5% worldwide. Additionally, the price of acrylic acid is currently increasing, as you can see here. This makes our market very large. Currently, acrylic acid is produced through propylene, as shown by the first equation on this slide. Our process will be using propane as a feedstock. So why use propane now? What makes this process viable? There are two main reasons. There's an increase in hydraulic fracturing, which produces a lot of natural gas, which has decreased the price of propane down to 21 cents per pound. In comparison, the price of propylene is approximately 72 cents per pound. Thus, it makes sense to use the cheaper feedstock. Additionally, there's been advancements in mixed metal oxide catalysts such as molybdates. Previously, it was very difficult to produce an unsaturated acid such as acrylic acid from a saturated hydrocarbon such as propane because of the difficulty in maintaining a high reaction temperature so the reaction rate is high while preventing a total oxidation reaction, which would mean a low yields of acrylic acid. The advancements in the mixed metal oxide catalysts have made this possible, and thus propane can be converted to acrylic acid in high yield. Dan will now talk about our design process in great detail.
Thank you, Amanda. So if I can get this to work. No. So this is our process up here. You can probably see it better on the left-hand screen. It looks pretty complicated. That's because it is. And so I'm just going to go over it in general detail for you and hit the highlights. So we come in, we have our feedstocks all the way on the left. That consists of propane, which comes from a pipeline. It comes in as a highly compressed liquid. It's what you might use to fuel your grill. We get oxygen from a pipeline. That comes in as a highly compressed gas. We also are pumping some air in there so that we can get some nitrogen into the system, and that nitrogen acts as an inert. So those three feeds move and mix with a recycle stream, and all that moves into our reactor section. Of course, in our reactor section, there is a reactor. The reactor is filled with the catalyst that Amanda talked about, and a reaction takes place over that catalyst. Only about 10% of the propane is converted per pass through the reactor. So coming out of our reactor section, there is still a lot of reactant. And we do form a little bit of product, acrylic acid, some acetic acid, and also water. So all of that gas flows into our separation section that you can see all the way on the right. And from there, our product is separated from the reactant, and that product moves through a series of distillation columns, which further refine and purify the acrylic acid, which come down all the way at the bottom right there at a rate of 200 million pounds per year. As I said before, we also have water and acetic acid, so that comes out as a wastewater stream, and that'll be cleaned. That's going to be cleaned by FDA regulations. And remember that I said that only 10% of the propane was converted, so we still have a lot of reactants. So that's what you see coming out of the top. We have a small purge stream coming out on the right, and that's so that we don't have a buildup of nitrogen in our system because what comes in must come out, and nitrogen isn't reacting. But the bulk of it is recycled and sent back into the reactor. And this recycle stream is one of the important design schemes that we came up with that were really vital to our success. So that recycle stream, our reactor design, our heat and work integration, and our separation scheme, those are all part of our intelligent design that enabled us to build a successful plant. So our reactor design, very early on, we realized that we have a very exothermic reaction on our hands. You can see we produce about 120 million BTUs per hour. That's even with the small conversion rate of propane. Just to put that number in perspective for you, if you had that amount of energy to power washing and drying machines, you could do about 6,000 loads of laundry an hour. So it's just a lot of heat. So we do, because we're working with a catalytic process, we need to keep the temperature fairly constant. We don't want thermal runaway, but we do have all this heat, so we need to get rid of it. So what we did is we designed our reactor as a shell and tube heat exchanger. And obviously what that means is that it exchanges heat. So you can see an industrial model heat exchanger up here in the picture, and it has these bundles of tubes that are running, and they are filled with our catalyst. And not shown here, but would be there, would be a shell, and you would have another fluid flowing counter-currently to take up all that heat. So you could, in most applications of a heat exchanger, you might use something like cooling water or pressurized steam to either cool down or heat up your system. But using something like cooling water wouldn't allow us to effectively use this 120 million BTUs of heat throughout our system. So we decided to use an industrial material, a diatherm, which enables us to take this 120 million BTUs, pump it throughout the system, and heat up other blocks in our process. And that heat integration is another important aspect of our design that Rohan's going to tell you about.
Thanks, Dan. So one of our goals from the very beginning was to conserve as much energy as possible, both from an efficiency point of view and a profitability point of view. And so we used a heat integration and work integration strategy to do that. So firstly, for heat integration, we used the reactor effluent, which is coming out at approximately 780 degrees Fahrenheit, to preheat the feed instead of using steam. So we save on steam costs there. And then, like Dan mentioned, we use the diatherm to cool off the reactor, but we don't want to throw that heat away. So we use the diatherm to create a loop, and it takes that heat to other parts of the process, mainly the separation part. So we save on more steam costs there. And for the work integration strategy, like Dan mentioned, we have the oxygen coming in highly compressed. We don't need oxygen at 500 psig for our process. So we send it through a turbine, and that expands it and creates electricity, which we add back to the grid. So being energy efficient is great, but in an industrial process, it has to be economically viable. And so looking at the two investments we have here, the turbine for the O2 expansion saves about 260 kilowatts of electricity with a fixed cost of just under $400,000. That gives a payback period just under 3 years with an ROI of almost 40%. And looking at the diatherm heating cooling loop, that has a net savings in utilities, about $4 million, with a fixed cost just over $7.5 million. So that investment has a payback period just under 2 years with an ROI of almost 50%. So the next key design aspect for us was the separation. So a separation can be especially difficult if azeotropes exist. An azeotrope is a point of concentration that you can't distill through when you're trying to purify a mixture, and they occur due to interactions between the chemicals. So up here you can see a ternary diagram, and that shows the interactions between water, acetic acid, and acrylic acid. And the key takeaway from this is that in this mixture, which we have in our process, there are 3 azeotropes. That makes for a particularly difficult separation. But what we're really happy about is that we were able to devise a separation scheme that avoided all 3 azeotropes and produced acrylic acid at 99.8% purity. And that's not a trivial thing. That's definitely a difficult separation. We're very happy that we were able to do that. Now Kevin's going to talk about some other considerations for our process.
Thanks, Rohan. Finally, I wanted to briefly give you an overview of the other things we had to take into consideration when designing our process. First and foremost, we have safety. We do have hydrocarbons flowing through our process at a very high temperature, so in order to avoid creating any explosive mixtures, be bad for PR, we made sure all of our streams are well above the upper flammability limit of propane and oxygen, which required adding some inert to the process, as Dan mentioned at the beginning. In addition, our chief environmental concern was the wastewater stream that we're producing as a byproduct of the reaction. It's about 97% water and 3% other organic acids. We added the cost associated with sending that to an off-site treatment facility into our analysis, so we're also taking account of that. That will be handled according to all FDA regulations, as Dan mentioned as well. So finally, you have an overview of the process, but as Amanda mentioned, this is a feasibility study, and no feasibility study is complete really without an in-depth economic analysis of the process itself. The total capital investment, which is a combination of all of the process equipment, our catalyst, backup materials, and the required cost of capital on hand to run the process, comes out to about $100 million. Aside from that, you have the annual fixed costs, which are those costs associated with wages, overhead, things that don't depend on our output necessarily, are $23 million annually. In addition, the total variable costs are things that do actually scale with the production. So raw materials usage, the wastewater stream I just mentioned, any other utilities and the like, those come out to $111 million annually as well. Aside from that, in year 3, we hope to be at 90% capacity of our plant, which is again 200 million pounds of acrylic acid per year. So at a price of acrylic acid of $1.20 per pound, we expect to be at $216 million in revenue annually. This gives us a net present value at a rate of discount of 15%, to be $150 million, and an internal rate of return of 50%, and a return on investment estimated at about 58%. To get a better idea of how these numbers can change with our actual assumptions we made, we did a detailed sensitivity analysis as well. As you can see on the x-axis here, you have deviation from estimated value of each of the 4 parameters that we show on the right side here. And on the y-axis, you have the IRR, or the internal rate of return. Most notably, we want to focus on the fact that the product price is this blue line here. And you can see that if for whatever reason the price of acrylic acid drops below 30% of what we estimated it to be, which is again $1.20 per pound, we could see how the process wouldn't necessarily have to undergo some types of additional work integration strategies or other cost-saving metrics to help us to remain profitable. But you can see that there's still substantial wiggle room on either end of the graph where we're still profitable as proposed. Oops, sorry. That concludes our presentation. I just wanted to finalize by saying, the goal of our senior design project was to propose an alternative strategy of making acrylic acid that's not currently done in industry today. And through the work integration and heat integration strategies that were mentioned before, as well as our unique method of separation, we were able to make a process that's very profitable. Next steps for our idea would be to obtain a more detailed kinetic analysis of the actual catalyst that we're using, which would usually involve doing a lab scale experiment-based setup. And then that can be mocked up into a pilot plant size thing so you can get a better idea of understanding how the actual blocks behave in a real world setting. And then you can finally scale up to a full scale process as the one pictured here. In conclusion, I'd like to thank these professors and advisors without whom our work this semester would have been completely impossible. And we'd like to entertain any questions at this time.
Like you said, reactivating propane at hot temperature is pretty dangerous. So what other safety measures do you have to design in case something goes wrong with control?
We have multiple control valves throughout the process with a PSI drop of about 10 PSI per valve. In addition, we have each of the, we include the cost of establishing a containment unit around the reactor, usually probably made of concrete. In addition, since most of the process is in gas phase, we've costed having leak detection systems throughout the process as well. And I think all that combined would take into account a lot of the safety problems we have. To your point though, I mentioned the upper flammability of propane and oxygen. It's about 1-to-1, but our most oxygen-rich stream has about 5% oxygen and 20% propane. So we're well beyond any sort of exposure that might occur from that aspect.
A question about some of the underlying economics of the system. If you think about the economic attractiveness, is a lot of it coming from sort of the heat process, or is most of it coming from the lower feedstock costs?
Well, the fact that the feedstock that's currently used is propylene at 72 cents per pound, whereas propane is at 20 cents per pound, we definitely see a lot of the cost savings coming from that. To your point, the utilities, there's still further room to maximize the utility costs that we have in the process. So I don't think necessarily the process itself is what saves the most money, but just being able to actually make it cost effective from that standpoint, including the cost of the feedstock is combined what gives us the cost savings.
And the four key design aspects we discussed were mainly what got us to be profitable. So the price of propane is the driver for the initial examination. and the fact that this catalyst is now able to conduct this reaction. So.
Capital investment should that be determined with fixed and variable costs?
No, so the fixed and variable costs are the annual costs that are associated with running the actual facility. The capital investment is separate. That's what you'd have to put up front at year one in order to make the process, to set up the process and construct the actual plant. Sorry if that was confusing, I apologize.
Okay, thank you very much.